In this course we are going to give an introduction to machine vision using Opencv. Machine vision tasks are lately very much used in both applications and in embedded systems, and one of the most widely used tool sets or frameworks for this is the Opencv Library. The Opencv Library has existed for several decades now. I think that from 1999 was the first version, and it was maintained throughout the years. To use the Opencv library, we first need to import it, so we're doing this by importing CV2. I'm not going to cover how to install it on the web page of Opencv. There are a lot of tutorials on installing it. Also, Opencv supports Python, it supports C and C++, it supports Java and other languages, so it's quite versatile. In this course we're going to cover Opencv with Python. Besides Opencv, since we are using Jupyter notebooks, we're going to import pyplot, so that we can use this plot to show the images. Now the main command for loading images in Opencv is imread, and I have an image ready. It will receive an argument, a string, with the path to the image. This is the image, and let's load it and display the image. So with this plt.imshow of the image, it will take the image and display it. With plt.show, it will plot it on the notebook. Let's run this. So here is the image. As you can see, somehow the colors are inverted. This is due to the fact that the matplotlib is expecting BGR and not RGB image. The images are saved in 3 channels. So if I want to access some value in the image, I can do it by directly accessing it in the matrix. So when we load the image, let's print it out. We can see it. As we can see, we have triplets in the image, 3 values. This is the red, green and blue values. The values are between 0 and 255, which means 0 is the least light and 255 the most light. So 0 would be black and 255 would be white. This is 1 byte of information, 8 bits or 1 byte of information, which means that for each color value, red, green and blue, we have 8 bits of information that give us the intensity of each of the colors. We can see now here in the print that the image is printed out as a matrix, and in this way, if we want to access a certain pixel, we can do it by directly indexing that pixel. So if I want to print a certain item, I can go with its coordinates, let's say 10, 10, 2, and this will print out, let me comment this out, the exact value. If I want to, I can also do it like this. So I will have the same value directly in accessing the index, or like this, I can get the full value of the 3 colors. This is the 0, the 1 and the 2. So if I change it here with 1, I would expect 129 on the top. So we can actually access the exact values of the pixels from the image. Imread is a fine command that allows us to load several types of images. We can load JPEGs, bitmaps, PNG images, etc. It receives a second argument. If we write it as 1, it will read a 3-channel image, -1, it will read the depth of the image as it should be, and 0, it would read the grayscale image. Let me show the grayscale image now. I'm going to need the cmap command so that it properly shows the grayscale image. Here it is. So now I have a grayscale image and I can't actually access the 3 channels. This is why I get the error. So like this I would get the grayscale representation of the image, and this is useful if we want to process a grayscale image, which is applicable for a lot of machine vision applications. If we want the full image, then we are using it like this with 0. With 1 it will load the full RGB image. So to transform the image, to transform through color spaces, we can use an integrated command in Opencv, which is convert color or CVT color. So I will just directly convert this image. It is expecting the input image as argument, and then it is expecting the conversion type. So I'm converting BGR to RGB, just switching the red and blue channels so that they are displayed properly. This I don't need. So this will be the image as it's supposed to be shown. There are a lot of other color spaces that we can convert the images in, which have different usefulness and applicability. All of them are quite well documented in the Opencv library. If we want to set certain pixels in the image, we can use the imset command. So item set, and I can just give the coordinates. Let's go with, and give a value of 0, and then again show the image. I need the exact arguments to set that item. So 0, so a certain pixel will be set to 0. We can also select a subset from the image. Let's have another image to be like this, and I can get that image and visualize it. Here is that part of the image, so we can select a subset of the image and put it in another image. If we need some characteristics of the image, we can print them out. So this will give us the size of the image, and this will give us the depth or the type of the image. So here I have the size of the image, which is 30,000 pixels, and this is the type unsigned integer with 8 bits. So these are some of the characteristics of the image that we can set. I can also split the channels of the image, so I can get RGB split of the image, and then print out the sizes or visualize them. Let's show them. I'm going to need gray cmap and show just, let's say, just the red channel of the image, and here is just the red value. If we want to visualize just the green value, these are the green values of the image, and this will be only the blue values of the image. Another useful command in Opencv that we can use is if we would like to make a border of the image. That's the command copy make border. We sometimes want to resize the image to a certain level by adding by not adding additional information in it, just add some border around it. So we have several options. It's either border replicate, border reflect, border constant, or border warp. So let's try it out. I'm going to use the image 2 and add 20 pixels in each direction. These four values give us that, and then we're going to opt in for border constant just to display the image here. So I'm displaying like this. Here it is. I added a constant value around it. If we try some of the others, replicate, it will replicate the last pixel, reflect the last pixels, and warp, it will exchange the left side will go on the right side, top side on the bottom side, etc. So however we can make the border and add the additional pixels. Usually it's added with a constant and median of the values of the image. Another useful function is sometimes we want an empty image. So if I want to create an empty image, I can use the Numpy library. To import it first. So the Numpy library will allow us to initialize an image. I'm going to use the shape of the image. So if I print out here this will give me the exact dimensions of the image. So it's 100 by 100 by 3. This is the width, height, and the depth of the image, how many values we have per pixel. So to create a new image, I'm going to create it by using the numpy zeros command and give the same shape. I want the same shape and with the same destination type. This will create me an empty image. So if I want to visualize that image, I'm going to receive a black image. Here it is. On this black image there are also functions that allow us to draw something. Let's draw a circle. So circle, it will be IM3, and we place the center of the circle in as a tuple, and then we give the radius of the circle, let's say 30, and then we can set the color of the circle. Let's go with red one, and the other argument would be the width of the line. Let's go with 10, and here it will draw a circle, a red circle inside the empty image. In the documentation there are multiple functions like this, like we can have ellipses, lines, and other, which are well documented and you can find in the Opencv documentations. They are mostly used to draw and to emphasize parts of the images. Opencv is rarely used to actually draw something. Another nice function is, let's have add the weighted, where we can add two images. Let's add the second image, multiply it by half, and add this third image and then also multiply it by half, and we can display the result. here it is. So we added the two images, we practically blended one image into another. This is a nice function if we want to add the pixels from one image to another, or to blend the images. Otherwise, arithmetic operations between the matrices are also allowed, but the result won't be so great. So if I have something like this and then try to show the result, there is the possibility, not the result I wanted. Here we won't find anything because there is a possibility of an error and an overflow of the pixels. So if we want to add them, we must first convert the images and then do it like that. So to convert it, let's say im2 equals im2, convert it to float 32, then split them. In this way we can convert the image, and after converting it we need to divide it by 255 so that we can again display the image. Let me show this. So if I have it like this without the division, we have a floating point image which has values of 255. If I divide it like this, then it will properly display the images. So the pyplot will expect an image either between the values of 0 to 1 if it's a floating point, or between the values of 0 and 255 if it's unsigned integer value. Let's go with some other useful functions. So I'm going to create two images, both of them with the same sizes. I'm going to draw two circles in them. These are grayscale images. One has this circle, the other one has this circle, and now what we're going to do is introduce bitwise operations with images. Usually black and white images like this are considered masks in Opencv, which means that we have a region of interest which is colored in white, and a region that we are not interested in which is colored in black. These masks are usually a result of some segmentation or other more advanced algorithm that is already executed over the image, but sometimes we want to combine these results, and in order to combine them we are going to use the bitwise functions. First, bitwise not, it receives one image and gives as a result the invert of the image. So this is it, it received the first image and it gives as a result the inverse version of the image. As we can see, everywhere where it was white now is black, and vice versa. The other function is Bitwise Sent. The Bitwise Sent function takes two images as an argument, and the result is a Bitwise Sent. It means that whenever the two images are white, it will give white, and where the two images, at least one of the images is black, it will give black. We also have Bitwise OR. Bitwise OR combines the images by making a logical OR operation, so at least one of the images needs to be white for the destination pixel to be white. And we also have the Bitwise XOR function, which gives us this result. It gives white where the pixels are different. If one pixel is 0, the other one, or one pixel is 1, the other 0, then it will be 1, otherwise it will be 0. These are quite useful functions for combining the masks in the images. Another important thing is to measure performance of the algorithms. So we have for that the command get tick count. It gets the tick count from the processor, and if we want to have two times, we'll have t1 will be get tick count, t2 again get the count, and we can get the difference between them. And if we want to get it in seconds, we can use this get tick frequency. So in this way we can measure the performance of various approaches that we use. I would now like to compare, let's say, how fast is the access to the pixel. If we have let's access on IM1 this pixel, and also try to access that pixel using the array access like this. This will not give a good comparison because we are doing just one operation, which is fairly quick anyway. But if we want to do a more realistic estimation, then we would probably want to execute this a lot of times. So let's go like this for A in range 10,000. Repeat this 10,000 times, and also repeat the same for the other. It's a quite fast command anyway, so it probably won't give a good result for comparison, but for more complex algorithms, in this way you can measure performance and optimize the algorithm as much as you would need. Here we have, if I execute it multiple times, we're going to have different results, but usually it should be that the first type of access should be mostly better than the second type of access, although it's not like that all the time, because it depends on the operating system and on the machine that we are using to execute the algorithms. So to summarize in this video, we have introduced Opencv as a library, how to import it, how to read an image using the imread command, how to convert color spacing using the CVT color, and how to access subset of the image to get some region of interest of the image, how to display the images, how to add borders to the image, how to initialize an empty image, and how to draw circles, how to merge or add weighted two images, some arithmetical operations on the images, like we can actually do plus, minus, and other operations of the images, but we need to take care of the overflow all the time, draw circles of the images, as I said previously, and the bitwise operations, bitwise not, bitwise and, bitwise or, bitwise XOR, and how to measure the performance of the algorithms that we have implemented.